Let's start with the last lecture for today of Professor Gukov, who will give the second lectures on vertex algebras and quantum invariants of 3 manifolds and 4 manifolds.
All right, thank you again. So let me remind you what we did yesterday. So, oh, by the way, before I do that, so we're using the whiteboard, which will be the same for all of these lectures. You can share it or post it on the web page. And that's the one that I'm using. So here it is in real time. So you can navigate through this.
I posted the link to the whiteboard on the website already.
Excellent, thank you so much. That's perfect. And of course, participants are welcome to navigate this whiteboard at their own pace and leisure on their mobile devices. So I'll try to share the screen most of the time. Again, if I forget, remind me. And what we were discussing yesterday, apart from the big picture and general motivation, which can be served as a summary of even things that I won't be able to cover, we introduced a definition. So for each decorated graph of this form, and certain quadratic form as being basically adjacent symmetrics, we defined various integrals that are obtained by integrating simple rational function obtained by taking products over vertices and edges of the graph with a theta function associated to the quadratic form. So, of course, this definition may seem very random. In particular, you may ask, why did I pick the specific factors for vertices, edges? Why not something else? So this is exactly the question that we are going to answer next. So with this definition, I announced that there will be some connection to logarithmic vertex algebras. That's still to come. But this is for us to maybe to keep in mind. In the meantime, we were going through some more specific and concrete theorem, which discusses various properties of this kind of integrals associated to graphs. And some properties were that this, as an expansion on Q, converges. Another property, which is fairly easy to see, was that it has integer coefficients and form which is perfectly suitable to be character of some BOA. In fact, there was a very good question about positive powers. So there I made the remark that one needs to introduce the Dedekind eta function in the denominator, which is often dropped in normalization. So one either introduces this as part of the definition of the integral or in this relation to characters. And I'll return to this point again today as promised yesterday. But there are a couple of other bullet points on this theorem which are supposed to summarize properties of these integrals for various graphs, and that's our next destination. So in order to do this, I want to explore or compute some explicit examples. So again, I'm going to share a link to Mathematica notebook, which computes these integrals for negative definite graphs. So here it is again. And I'm going to share on the screen that same code. So you're welcome to use it, play with it. So for instance, here is an illustration of graph put as an input in this notebook. It computes various simple invariants, such as adjacent symmetrics, for example, its inverse. Since I emphasized negative definiteness, it computes the eigenvalues, so that's useful to check if we want something negative definite. And as a result, it spits out some of this Q expansion. So you can see that they're fairly elaborate and have indeed integer powers, integer coefficients, aside from this overall power of Q, which from the viewpoint of vertex algebra, we may think of as conformal weight. So for this particular example of this complicated graph and this outcome, I actually have no idea what kind of log VOA or VOA character it is. So I'm going to pose this as one of the open questions. I'll tell you classes of graphs for which log VOA has been identified, but the main reason I'm giving these lectures is because there are, of course, many more where there is an opportunity for research and saying something new. So, in fact, way more examples or classes where things are not known rather than where they have already been known or settled. So I'll actually explain, let me do a simpler example here in front of you, which is where this all started. So the way things were defined, they had nothing to do with Vertex algebras. So far, this definition was either combinatorial or, if you wish, topological. How it's connected to topology, we'll see later. In some sense, the appearance of anything related to vertex algebras was a surprise. So let's see how it happened, and this is the concrete example on which this actually happened. So I'll put a very simple graph which has only 4 vertices. That's why I removed a bunch of others from this more complicated example. So we'll label them 1, 2, 3, 4. So it means that 1 is connected to 2, 2 is connected to 3, and 2 is also connected to 4. And here are some of their labels. So then I'm going to run this notebook and see what it gives. So first, let me scroll back up. First, it illustrates this graph. As you can see, this is a simple trivalent graph with only 4 vertices. It's a little bit more interesting than the homework I suggested yesterday. I'm not sure if how many of you or if any of you did this kind of thing by hand. So that's it's doable. It's actually not too hard, but of course a little bit more advanced compared to previous homework. Here is adjacency matrix, it's negative definite, so all of that checks out. And here is the answer. So here I'm expanding it only up to q to the 100th power of q. So let me maybe change this to 200, for example, in the next round of computation. But first I want to save this expression. So copy this answer and save it. So let's say this is a bit too small, so let me try to make it a larger font. Okay, how about this? So again, we don't have eta function in the denominator yet, so it has to be divided by that. But what we see, if you wish, in the numerator, which needs to be divided by q infinity, is expansion with integer coefficients, which are pluses and minuses. Of course, this is not the general fact that, plus minus ones, that more generally there will be other coefficients, not just plus minus ones or zeros. But this is looks not terribly bad. Coefficients are integer and some overall power is fractional. So I'll say more about this function later, but at this point it doesn't tell us much. So what I'm going to do, I'm actually going to modify the graph. So we'll say that we'll now have 5 vertices, and I'll change their...
Is that function a theta function?
No.
No?
No. But you're asking very good questions. So in general, in some sense, before we I'll pose this as a problem or open question today, later in my lecture, namely for general graph gamma, this one could be an example, tell me what the function we get. What kind of function is it? So in general, that's not known. And this particular one, I'll tell you the answer to this. This one has many presentations. It will happen to be Q hypergeometric function. In fact, it's not exactly a theta function, but it's one of the few examples that Ramanujan wrote in that letter to Hardy 101 years ago. Oh. So that's already good news. So it's
so it's a mock theta function.
Huh?
So it's a mock theta function.
Exactly,
Okay.
exactly. It's a mock, or more precisely false theta function. Exactly. Okay. So question is, what happens if I take some other graph or more complicated ones? Again, for general graphs, this is not known, but that's where excitement starts, basically. So right. So let me modify this graph by adding one more vertex and changing some of its label. So now it's going to be a completely different graph. I'll ask Mathematica to forget everything that happened a moment ago. So here we go. And we'll try to compute it one more time. So, and see what we get. So before we look at the answer, this is the new graph. As you can see, it now has 5 vertices. So we actually completely changed the graph. So integral in the integral notation is now multiple integral over 5 variables. So previous one was over 4 variables. Again, this is negative definite, that checks out. But if you look at the answer, we see that the answer didn't change. So I increased my precision. So here I'm doing expansion out to higher powers of Q. But it doesn't matter. What you see very clearly, hopefully, if my resolution is good enough on a screen in the auditorium, is that the answer is still just the same. So therefore, at least for some graphs, the result does not depend just on a graph, but it depends on equivalence classes of graphs modulo certain relations. And this is an important point. So that's the point I want to illustrate. We can play with this more, so I encourage you to do so. I think, well, maybe I'll do just one more time. So I'll ask it to forget everything, and then make another modification. Say, let's add one more vertex, for instance, connect 5 to 6. So just for fun, I'll change this to 2, add another one, and let's evaluate, see what happens. It's getting longer. We can, for example, try some linking diagrams as graphs, or connectivity graphs of your friends on Facebook or other graphs, and see what kind of answers we get. For this particular one, which now is even bigger, the answer is still the same. So it didn't change. So we clearly see that there are some equivalences. So that's good enough for experimentation. I'm going to stop sharing this screen and go back to my whiteboard. Here it is. And we'll try to formalize this property in the following way. So another bullet point is waiting for us. So what we discovered just a moment ago, sort of experimentally, is the first indication that this problem has anything to do with low-dimensional topology, namely 3 manifolds and 4 manifolds that I'll explain later. Namely, we discovered invariants, that this answer is invariant under so-called Kirby-Neumann moves. So I'm going to give you a definition of Kirby-Neumann moves in a minute. So next thing will be definition. So maybe let me save a little bit more space. So lower, I'm trying to write definition, trying to define what these are. But before I do that, I want to point out or complete this last bullet point in this theorem by saying the following. So out of all these properties that I'm trying to list here, some are simpler than others. For example, first two were fairly straightforward by either like ratio tests or examination of the definition. It's not hard to prove that coefficients, for example, are integer. So this invariance under Kirby move is perhaps the first set of non-trivial properties, so that requires a little bit of manipulation of these integrals and understanding their better, deeper structure. So that's non-trivial part of the theory, but conceptually what it means that we found invariant of three manifolds, because in a way I'll explain it later, that three manifolds are defined by certain construction. In a combinatorial way, one basically assembles certain pieces together or constructs in a certain way. But then in every way of constructing three manifolds or four manifolds, one has certain equivalences which relate different routes to the same destination. So familiar examples involve, for example, Reidemeister moves in the case of knots. So these are usually described by planar diagrams, but then diagrams related by Reidemeister moves represent the same knot. Equivalently, one can talk about braid relations in a braid group. And in the world of three manifolds and four manifolds, that's what I'm going to teach you in this lecture and to some extent next time. We have analogous constructions and relations. Usually, one tries to make these relations rather small list so that things are fairly efficient, and this Kirby-Neumann relations or moves are analogs of Reidemeister moves. But then the point is, once there is certain object that is invariant under these moves, it basically is guaranteed to be topological invariant. So implication of this bullet point is that we got ourselves invariant of three manifolds. So that's already interesting, and it's some kind of Q-series invariant of three manifolds. So natural question to ask is, how is it related to something familiar, something that we perhaps have seen in topology or quantum topology? It turns out that for generic Q, this Q-series is new, but one can compare to more familiar invariants by taking the limit where Q goes to root of unity. So as Q goes to root of unity, e to the 2 pi I over k, this gives some familiar invariance. Quantum group invariants that are usually defined using quantum groups at roots of unity. So quantum group invariants of three manifolds together with knots. So this include so-called Wittmann-Reshetikhin-Turaev invariants, abbreviated as WRT. More interesting or exotic invariants due to Akutsu, Deguchi, and Otsky, called ADO invariants, so-called CGP invariants, Rochlin invariant, and so on. So all of these have to do with taking Q to be a root of unity and our standard invariance of three manifolds. So as a homework, I want to suggest explore or even, so I gave you a way to compute this Q-series invariance for general graphs. So construct or explore examples in the simplest limit where q goes to root of unity, namely q goes to 1. So what you will get is a very simple 3-manifold invariant. It's still non-trivial and interesting, but just like q equals 1 is the simplest root of unity, it will be nicer and simpler than many of the other ones I mentioned. So explore q equals 1, and hint is that you'll get very simple familiar invariant. Maybe try to identify which one it is. Okay, now back to Kirby-Neumann moves. So we're slowly learning. Again, in these lectures, we'll be kind of learning in parallel two things. Some facts about vertex algebras, especially logarithmic ones. I'll assume that certain things about standard or familiar traditional vertex algebras are reasonably familiar, and many of them are covered in other lectures. And we'll be also learning some bits and pieces of topology. So this is topology piece, which I'll finish very soon, and then we'll transition to logarithmic VOA. So what are the Kirby-Neumann moves? So first of all, if you see a piece of graph which looks like this, so basically a vertex connected to other things, which is fairly generic, what you're allowed to do is consider either operation called blow up. So this is the name of the operation, or blow down, which produces a different graph. Where this vertex remains connected to everything it was connected before, but you're allowed to change its coefficient, this integer that decorates it, by plus minus 1, and that plus minus 1 is correlated to decoration of a new vertex which got connected to it by a new edge. Okay, that's exactly, of course, that's exactly the operation I did in this experiment in front of your eyes. So we were basically doing a sequence of blow-up operations. And claim is that in a way that I'll explain either later today or tomorrow, 3 manifolds and 4 manifolds constructed out of this data of graph are equivalent as long as graphs are related by these moves. Okay. So another version of this move, also called blow up and blow down, is the following. It involves two vertices which are connected by an edge. So in fact, that's kind of also generic situation in a graph. So if you have A1, A2 as decorations of these two guys, we can consider analogous equivalence relations going either direction. This is totally fine. Where we keep the rest of the graph intact, but like in the first case, we create additional vertex and additional edge labeled by plus minus 1. And we change the labels of the other ones accordingly. So this becomes A1 plus minus 1. This becomes A2 plus minus 1, depending on the sign of the new one. Is this clear? Any questions? Okay, there are a couple of more moves. There's Kirby-Neumann moves. So imagine that you have, so all of these moves, by the way, they share one essential property that they involve creating or destroying new vertices, but their labels are very special. They're plus, minus, ones, or zeros. So generic labels are not allowed to be created or destroyed. So imagine that you have a disjoint union of several pieces in a graph that sometimes happens and can be achieved by these moves. So you may have some graph, let me call it gamma 1, and so on, say gamma s. So we have some number of number of disjoint pieces. So this is disjoint union. So then all of this can be reconnected, and we'll have the same content of gamma 1 through gamma s unchanged, so that will stay the same. But they'll get connected to a new vertex, which may be labeled by any a as long as the next one is labeled by 0. So this is an example where, so all of them get connected. So this illustrates that 0 is also a special value, just like plus minus 1 was special in this blow-up relations. And finally, the last non-trivial Kirby-Neumann move is the following. So it's analogous to the previous one. So if you have, let's say, a vertex connected to a bunch of things, you can sort of resolve it very much as, let me reserve a little bit more space, very much as in this blow-up, blow-down relations. So let's see, probably here is a good place. Let's say, strangely enough, my whiteboard leaves a trace, so I'm trying to figure out how to remove that component. Okay, let's see. So imagine that there is a vertex here. So I apologize. Somehow it didn't update properly. There is a leftover from the previous. Sometimes it doesn't sync, I guess. So what happens here is that we keep the rest of the diagram unchanged, create a new vertex, and connect it to the rest of it. So let's see. This should work. So the labels, the labeling here is such that if on the right I have A1, 0, and A2, as in the previous case, then when I do this blow down, it changes to, the labeling changes to A1 plus A2. Okay. So now the claim is that you basically can verify that with this definition of Kirby-Neumann moves, the integrals that I gave you are invariant under it. So the statement again is that we don't compute a separate value of these integrals for each individual graph, but we compute it for equivalence classes grouped by these equivalence relations. So any questions at this point?
In the third rule, what does it mean exactly? Like, I connect them any way I want, or does it have, like, when I connect the separate components of the disjoint components of the graphs, when I connect them to the other point?
They all get connected once by you mean inside gamma 1 or?
Yeah, inside, like I can connect them to any single vertices of these graphs, or there are some?
Yeah, to some single vertices in this graph. If I remember correctly, it doesn't matter which one it is. I may be mistaken, but yeah. So I believe it doesn't matter. In fact, also the value of this little a on the new vertex doesn't matter. So part of the reason is that, as you can see, the 0 is much more destructive than plus minus 1s, which were up there. So plus minus 1s require some correlation, and they're kind of sensitive to the rest of the stuff. But the 0 basically destroys the entire part of the graph. And I believe for this reason, it doesn't matter how these things are connected. But yeah, that's it, just in case it would be good to double check. So this is part of kind of typical textbook on Kirby moves, or 4-manifold or 3-manifold topology.
So can I ask a question? Does this mean that we can always choose a representative for graphs where there are no vertices labeled 0 and plus or minus 1?
Basically, yeah. So right. So what this Kirby-Neumann moves mean in practice is that if you see plus minus 1s or 0s, you can immediately apply some of these relations and get rid of them. Conversely, if you want to connect two completely different graphs, sometimes it happens that graphs are labeled by values of AI which are not 0, plus or minus 1. You may create additional new plus minus 1s or 0s and then in the end destroy them in a different order. So that's a typical application of these rules, or how people play this game.
Okay, sorry, maybe stupid question, but your moves, they preserve the condition that Q is definitely negative? And is there a way that your invariant also has a depend on some lattice in the co-K of Q? And okay, how is preserved the moves?
Yeah, that's a very good question. So I introduced it this way just for simplicity. So this soon I'm going to relax this condition, because in the world of 3 manifolds or 4 manifolds, we may want to consider any adjacency matrix which may be degenerate. In fact, it may have lots of 0 eigenvalues. And soon I'm going to allow this. So therefore, at present, we can apply this Kirby-Neumann moves so that we keep the condition based on what we learned so far, but these moves are completely general. So the way I stated gave you this definition, apply them to, later on, once I explain generalization, you can apply them to, the moves are going to be exactly the same to more general context. Does it make sense? Did I answer the question?
Yeah, I think so.
Well, if I take a move, is there a natural bijection between the co-K of Q of the guy on the left and the guy on the right?
Yes. Yeah. So this Kirby moves, if determinant of adjacency matrix is non-zero, then it's a very good question. So we're gonna slowly move our way toward 3 manifolds and 4 manifolds. So let me maybe now make a remark. So below of all of this, I'll make a remark. So it may be a little too early, but since you asked, let me address it. That what we call, so first of all, kernel of Q is indeed preserved if determinant of Q is non-zero. But again, later on, I'll allow even determinant being 0. What is kernel of Q in notations of 3 manifold? This is nothing but H1. of a three manifold did not appear yet, but when it will be a abelian group, which is first homology of a three manifold with integer coefficients. So for instance, when Q is unimodular, so determinant is 1, we know that we work with homology sphere. Okay, and see, the point of this Kirby-Neumann moves is that they preserve a three manifold. So sometimes these moves are called the 3D Kirby moves. So in particular, they preserve H1. So therefore, as a corollary of Kirby and Neumann, this kernel is actually preserved by these moves. So the example I showed you, so the example that we saw associated, so it was this graph, or in fact, then we did a bunch of blow-ups, and of course there are many other graphs in this equivalence class. So center was labeled by -1, this was by -2, -3, and -7. So this corresponds to a particular three manifold called Brieskorn sphere, and denoted sigma 2, 3, 7. And as you can see, 2, 3, and 7 show up as labels of external, this three vertices away from the center. So what I mentioned is that for this guy, we got something. So now enough for topology for now. We'll come back to three manifolds and talk about it later. But I quickly noted when you asked me about what kind of function it is. So I'm glad I put you in a set of mind where, that's why I shared this Mathematica program. You can play with it and ask the same question for complicated graphs like this H-shaped graph, which was initially in this Mathematica code and so on. What kind of function do we get as a Q-series? So in this case, this turned out to be one of the examples due to Ramanujan. Of course, he wrote only a couple of dozen of special functions. So by playing with these graphs, we know that we're quickly going to get outside of his set. So it's hopeless to expect that we're just going to stay in a territory of something as simple as mock or false theta function. So it's going to be much more interesting. And more importantly, what we obtained for this example, since this is all about vertex algebras, let's now go back to vertex algebras. I can rephrase the statement that for this manifold or this particular graph, this Q-series is actually a character and again, I'll put 1 over eta in the denominator here, but as is often done, I'm not going to be super careful about this normalization. So we either include it in the definition or not, but I'll often probably omit it, and I hope you forgive me. If it's confusing, I'll be happy to restore it. But the point is that this special function turns out to be a character of log VOA, logarithmic vertex algebra. So that's what we're going to discuss next. Namely, this vertex algebra has a name. It's so-called 1, p singlet algebra. Singlet algebra with a specific value of p equals 42. So I remember when Mike Friedman heard a talk about this. So this is actually an example where it all started. This was maybe 4 or 5 years ago. And Mike Friedman, when he heard this, he said, oh, 42 is a very special number in the Hitchhiker's Guide to the Galaxy. It's the answer to the meaning of life. So, that's of course true, but here it's just a special feature of this particular example, and has to do with the fact that product of 2, 3, and 7 is equal to 42. We can compute this Q-series for many other graphs where you can decorate these vertices in any way you want, and then of course it's not going to be 42. So connection to this Hitchhiker's Guide is fun and interesting, but limited to the special example. But connection to log VOAs turns out to be deeper. And that's what I'm going to explain next. In particular, let me try to explain what this so-called singlet log VOA is. So it's labeled by integer p. So now we are moving to sort of next discussion topic or point, log VOAs, logarithmic vertex algebras. And before I explain what a singlet is, let me summarize some of the key features or related properties of logarithmic vertex algebras. So first of all, they have logarithms in OPEs or correlation functions. So in other words, when we consider OPEs or products of vertex operators, we usually get poles, something like 1 over z minus w to some power, but in this case we get logs. We also get logs in a sense of representation theory. So in general, log VOAs have non-semi-simple representation theory. Namely, we have Jordan blocks associated with the representations which are reducible but not indecomposable. And in other words, we have projective representations. So thinking about this Jordan blocks is kind of analogous to having logs. So they're monodromies, in other words. You can think about it this way from sort of Knižnik-Zamolodchikov perspective. So there is a third sense in which logarithmic VOAs have logs, if you, which is perhaps more related to what we're discussing so far. If you look at their characters, you know that for usual vertex operator algebra, characters transform as vector-valued modular forms. And they're nice vector-valued modular forms in the sense that these are traditional textbook transformations. Whereas the fact that we already encountered this example through Ramanujan, or a character of this example through Ramanujan, suggests that modular properties of characters of log VOAs in general are not quite traditional modular. So in fact, they involve log of q, which is tau. So modular properties, I'll just say unusual modular transformation of characters For instance, they involve log of q. That's another sense in which we're talking about logarithms, which is tau. So that's of course not the usual feature of usual characters. So these properties are closely related, and again, I'm not going to explain their deep interconnections. This is to some extent explained in the references I mentioned and references therein. So there is huge literature, but I'll show you a couple of examples of these log VOAs, which are most relevant to present discussion to clarify, for instance, what is this so-called 1, p singlet? Okay.
Can I just ask a quick question about the previous example? So you say 42 is not special in the sense that there's infinite family where you could take any 3 integers and you would get the 1, p singlet with p being their product. Is Is that right? Okay.
Yeah. That's simplest infinite family. And at first, so now this is a theorem. In fact, it's precisely in one of those references I mentioned. But at first, it was just at the level of a few examples. And I have to say that 4 or 5 years myself, when I came across this, I didn't know much about logarithmic VOAs in the first place. So I've heard a lot about them from my colleague Boris Fagan, but I didn't pay much attention. And B, to me, this observation that, okay, we get some character of log VOA seemed sort of, kind of like an accident. Same way one can probably look at Nakajima's observation back in '94. It was only for instantons or sheaves on some LE spaces. These are extremely special given by declassification. So one could say, okay, it's nice that we get some characters, but there is no reason to expect it should generalize to other 4 manifolds, in his case. Now we know, of course, that's not the case, and the same thing happens here with this 3 manifold. So the further one digs, more evidence one finds that there is indeed this connection between 3 manifolds and log VOAs, and that's precisely the reason why I mentioned already last time in my first lecture, some of the experts may already start thinking how to define a log VOA given a general graph gamma, even negative definite, even with that simple assumption that we made before. So I'll also come back to this later today.
Oh, yeah. Thanks.
But yeah, you're absolutely right. So that's, for instance, you already anticipated the entire infinite family labeled by coprime integers P, Q, and R, for example. That would be Brieskorn's sphere of a certain kind. Right, so let's see. So why is this interesting? So maybe once we're discussing this, I should share a bit of philosophy, which again, I learned from Boris Fagan. So he thinks about log VOAs as a suitable generalization. I think I mentioned this already briefly in answer to one of the questions yesterday when we talked about like chiral algebra versus log VOA. So there are, of course, extremely special rational VOAs. So these are super nice. So let me draw a Venn diagram. So rational VOAs, then we'll see it somewhere in the center of this diagram. So they're contained in a class of just vertex algebras, not necessarily rational, which will be a further layer of this onion or Venn diagram. So then, in particular, here I'm assuming that they're unitary, for example. But then the biggest shell, and then one can refine this Venn diagram in many different ways, would be in terms of logarithmic VOAs. And that's why to Boris and probably to many others, these are extremely interesting algebras because they're in some sense most generic. And then the way he likes to emphasize this is if you throw a dart in the landscape of all possible VOAs, we're most likely going to end up with logarithmic ones. But this is a two-edged sword in the sense that it motivates studying log VOAs, which are being developed. I mean, another reason for me to bring it up in this meeting is that this is cool cutting-edge development because we don't have a theory of most general logarithmic VOA. And the reason is that being more generic, they're also in general harder. So there are some simpler examples of log VOAs which one can find under the Lamppost. So this is kind of called the Lamppost Principle, that if you look among the simplest possible ones, so this is the Lamppost, and it shines light on some simple area which is highlighted. So then, of course, it's easy to find simpler examples somewhere here. And I'll describe what these are in a second. But in general, if we ask for completely generic logarithmic VOA, then we know very little. In fact, in particular, even at the level of characters, which of course is a very simplified side of the story, we know very little about their modular properties or transformations and so on. So I'll tell you just a couple of families of examples, including this 1, p singlet that already showed up, and then we'll try to make this connection between 3 manifolds and log VOAs deeper, because the point will be that to general 3 manifold, including in particular any decorated graph like this graph gamma, there should be a corresponding log VOA. So that's the goal. And then I don't think I'll make it to 4 manifolds, but maybe I'll make some comments in the last lecture on Thursday. So examples. There are in textbooks, or there aren't really textbooks as far as I know on log VOAs, but there are many very good lecture notes. There are usually 3 infinite families mentioned. So let's give them a name and then expand on them a little bit. So one class of examples is a generalization basically of BC system. These are symplectic fermions. So usually abbreviated as SFD. D stands for number of copies of symplectic fermions, and this is non-negative integer. And all these algebras contain Virasoro. In particular, Virasoro central charge for this family is minus 2D. So immediately you see that it's negative. So all this, due to all the above kind of pathologies or interesting properties of logarithms appearing all over the place, these algebras are typically non-unitary. So another family or 2 families that already mentioned, one is called singlet. It's infinite family labeled by integer p, which is meaningful when p is greater than 1, so it can be 2, 3, 4, and so on. And this one contains Virasoro with central charge 1 minus p minus 1 squared over 6p. And 6 in the numerator. 6 appears here. That's the usual minimal model central charge when minimal model labels are 1, p. And then there is analogous model called triplet. Also 1, p triplet log VOA with the same central charge. So maybe I'll just say it here, same value of C and same value of P. So there are various generalizations. In general, this triplet and singlet model can be generalized to P, Q, just like minimal models, and also they're naturally labeled by AD Cartan types. For me, most of the things, as I mentioned in the beginning, are associated with Cartan type A1, namely SL2. So what is this triplet? So let me I mean, it has several presentations. Again, many details can be found in that reference I mentioned earlier, but I'll try to summarize highlight some of the key properties. So let's introduce the usual notations where I'll introduce alpha naught to be alpha plus plus alpha minus, and alpha plus is going to be square root 2p, and alpha minus is going to be minus square root of 2 over p. Then we can start with lattice VOA. Lattice VOA associated with a lattice lambda, which I'll take to be rescaled lattice of the root lattice of SL2, square root of p here, root lattice of SL2. So altogether, this is basically a rescaled lattice, which is one-dimensional lattice. And in terms of this, so now this lattice VOA has two screening operators, usually called long and short. So S plus is the long one. And explicitly is given by integrated version of the vertex operator e to the alpha plus phi, where phi is the free boson and the free field realization. And the short one, I'll call it S minus, is integrated form of e to the alpha minus phi. So this one is a short one. So the screening operators, they commute with a stress energy tensor or a conformal vector, whichever notation you prefer, that generates Virasora. So they commute with T, and the explicit form of T is the following. It has the usual Sugawara type term for single U1, so it's d phi plus this alpha 0 that we introduced a moment ago divided by 2 del square phi. So in particular, you can verify that this T, its own commutation relations produce Virasora with a central charge as mentioned before in terms of value of P. And also, as claimed, that this screening operators S plus and S minus commute with T. Okay. So then with this preliminaries or notations out of the way, we can define this triplet algebra in several different ways. So first of all, we can say that triplet, or to be more precise, 1, p triplet associated to SL2, because we used the root lattice of SL2 in the beginning of this construction. Remember, it was rescaled by square root of p. So triplet log VOA is going to be defined as kernel of the short screening operator, kernel of this operator S minus on lattice VOA, original one. So this construction these days is often called Fagin-Tipunin construction. And can be generalized in many different ways. For instance, if you have some general lattice VOA based on lattice lambda, associated to some lattice lambda, then you can consider kernels of various screening operators. Let me call them SI, and we consider intersection of all of those over I, and then we declare that this is going to be our new algebra. So this sort of construction.
Can I ask a question?
Yeah. Mm-hmm.
I'm just a bit confused. You start with a lattice vertex operator algebra, then you take a kernel in it, so it's a sub-algebra. But then why would it, so the OPEs will not have any logarithms? I don't understand.
Perhaps I can make a comment. We were saving this towards the end. I think this is a difference between physicists and mathematicians. So the triplet algebra is a vertex algebra in the usual way that we call a vertex algebra. But it has simple modules where the L0 has non-trivial blocks. So it's not diagonal. So if you compose intertwining operators between the simple modules, you find singularities that are not rational. So I think physicists call OPEs even those compositions of intertwiners, not only the ones that are coming from the vacuum module.
So it is a vertex algebra.
Yeah, the triplet vertex algebra is a vertex algebra, but if you start composing intertwiners of simple modules, you find more singularities than just rational functions.
Well, so in that sense, I'm happy to use any terminology, whichever is more comfortable, but that's precisely the reason why I think some people would not call it vertex algebra, because indeed you encounter modules which are not just usual functions. I mean, contain logs. Yeah. Right. So I'm happy to adopt whatever terminology one uses, but this is clearly outside of usual kind of conventional setup where we have nice modules. So there are more modules. Another way to say it is that we're making algebra which is smaller, but of course, therefore, it will have more representations, and among them, I mean, a priori, representations may still be nice. For example, affine W algebra may be also found inside VOA, but this lattice VOA. But here, what happens is that because we take only kernels of some operators rather than cohomology. So, for instance, construction of Felder of minimal models involves taking cohomology of BRST operators or screening operators. And here, in this so-called Fagin-Tipunin construction, one takes only kernels. So that's maybe another reason why conceptually one should expect something like logarithms appearing all over the place, or Jordan blocks, rather. These two are related.
Can I ask something? Sorry if it is too basic, but can you recall in 2 words what does it mean to take the kernel of a lattice VOA, please?
Well, you basically it's everything which is annihilated by this particular SI. So in the simplest case where P is equal to 2, this operator is, I mean, there is a close relation to the symplectic fermion. So you can think about this as a fermion itself. I mean, this SI, and it squares to 0. So you basically literally just take everything that has 0 product with this, on which it acts with 0. And again, I apologize if you prefer it in slightly different language. There are many good reviews, including the surveys that we had in this paper with Fagin, for example, and then many references therein. So I suggest to take a look at those. So here I'll just try to kind of summarize it, but I'm not sure if I'm using the optimal notations or conventions.
Thank you.
So maybe, I'm not sure if it will help, hopefully it will. Another way, so this was one way of thinking about triplet VOA. So far I'm kind of clarifying or commenting on what a triplet is. There is another way to think about it, at least in the context that we're discussing. So that same triplet log VOA. So previously I was starting with something bigger and then making taking a kernel, but here you can think about this as an extension. So it's extension of Virasora by an SL2 triplet of Virasora primaries. That's the reason it's called triplet. Of Virasora primary fields. So generated by T as above and operators that I'll call W plus, W minus, and 0. W plus, W minus, and 0, which have Virasora weight 2p minus 1, so it depends on p. And explicitly, these are the following. So W minus, of z is just e to the minus alpha plus phi. W0 is a commutator of S plus with W minus, and W plus is S plus with W0. So these operators, W plus, W minus, and W0, their usual Fourier expansion, when we do the Fourier expansion, have 0 modes. Or operators which are at the lowest powers of this expansion. I'll call them 0 modes. They generate a global symmetry, namely automorphism of this triplet algebra. So automorphism of this triplet is non-trivial and is a group PSL2C. So the reason this model is also interesting is that it has this this algebra has non-trivial automorphism, and when we talk about singlet, so that this allows me to quickly define what a singlet is. It's basically the invariant sector of this triplet with respect to this PSL2C. In particular, at the level of characters, characters for the singlet which are just functions of Q. And again, singlet can be also labeled by 1, P and associated with some root system. These are constant terms of the type that we saw before of triplet characters. So, and triplet characters are in general functions of Q, which is, so maybe I'll write this in a second, and some variable x, which is associated with this PSL2C symmetry. So these are generalized or sometimes called twisted or twining characters, where we also use the symmetry. So in general, we have chi, which is for general VOA, of course, it's defined as trace over, say, vacuum module or some other module of Q to the L0 minus C over 24. But one can also insert here some group element G. So this is a type of twisted or twined character. Again, I don't know what the usual terminology you prefer, but the point is, because triplet has this additional symmetry, we can consider these generalized characters, which now will be functions not just of Q, but may involve this variable x. And singlet characters are essentially constant terms with respect to this symmetry. So that's how the singlet character, for example, for p equals 42 that we encountered earlier is obtained. So does this make sense? So the symplectic fermions are probably the easiest of all of this in terms of VOA. So let me say a few words about this too. Symplectic fermions. So these are pairs of chi alpha. You can think of these pairs as pairs of B and C, or other derivative of C. Or also as, let me move it here. As d theta alpha, such that commutation of thetas will have logarithms in there, but commutation of chi's, these are usual fermionic currents, so chi plus of z, chi minus of say w, will have OP, which has the usual form 1 over z minus w squared plus something non-singular. So you may notice, so if you have d pairs of such guys, you'll get exactly this symplectic fermions SFD, which have central charge minus 2 times d. So for d equals 2, this is, or for d equals 1 for a single pair, this is just minus 2 in the simplest case, when you have a single copy of such symplectic fermions. And this happens to be exactly the same value of central charge as triplet log VOA for p equals 2. So therefore, you may suspect that the two are related, and indeed, it turns out that there is a connection, and triplet with p equals 2 is an orbifold of symplectic fermions by Z2 symmetry, which basically projects out odd. I mean, symplectic fermions is a super algebra. It has even an odd part, and this orbifold basically projects out the odd part, whereas triplet is even, or in physics terms, bosonic algebra. So they obviously cannot be equal, because in general one would require spin structures if you work on general surface, whereas the other does not. But they're related by this orbifold construction, or bosonization and fermionization, as it's sometimes called. Now, one more fact that I want to mention about triplet is that to sort of conclude this summary of various facts, is that among because this algebra is algorithmic, it's sometimes tricky to ask what kind of representations we should or should not include. Especially in these infinite families, this is well studied, but if we're given garden variety random logarithmic theory, this is a good question. So in this particular context, so for triplet, 1 comma p triplet has 3p minus 1 representations, which are called atypical. And these are, in some sense, rather special. So these are the ones which play a role in connection to, for example, singlet, and that representation whose character we found in this sigma 237 example, and similar things you're going to find in various generalizations if you study these Brieskorn spheres. And these representations, for example, have conformal dimensions or scaling dimensions, or weights with respect to conformal vector, which are the following. So let me call the conformal dimension, or this scaling dimension, delta. Just like central charge, it's not going to be positive. So if theory is unitary, it has to be a positive number. Here it's not going to be positive. And for p equals 2, which is related to that symplectic fermion case, the values are minus 1/8. So that's already negative. There is 0. That's usually the vacuum trivial, or like sorry, not trivial, but vacuum or identity representation, but it repeats itself twice. So that's the manifestation of the Jordan block structure. So there is another 0, which I'll denote with a tilde. There is 3, 8, and 1. So in total, the expression I gave you is that there are 3p minus 1 of them, and for p equals 2, so this is the answer for p equals 2, there are 5. So analogous list for p equals 3, and then I'm not going to give you the most general one, is minus 1/3, minus 1/4, minus 1/4 again, so it repeats. I'll put a tilde here. There is 0. 0 again repeats as in the previous case, so this is again manifestation of this Jordan block structure. 5/12, 1, and 7/4. And in total, again, we get 3p minus 1, where in this case, this is for p equals 3. So this is the list of weights or scaling dimensions. So these are some snippets and some facts about basic examples of log VOAs, but in general, motivation here is to construct many more new examples. And therefore, so we'll talk more about it next time, but already at this point today, I want to now come back to these graphs and ask a number of questions or problems. So this is not like homework problems, which are easily doable, but these are more problems for actual work. So what could be now the strategy? So we saw that in some examples, this three-manifold invariants turn out to be characters of log VOA, at least simple ones like this singlet and triplet log VOA. And this indeed is the case, or well understood now, for graphs which are of the form like this, which have one trivalent vertex and 3 legs of arbitrary length. So for graphs like this, we get that this equals to chi of corresponding or some singlet log VOA for some p or its extension, which in general is hard to detect, but that's sort of a statement. Therefore, one can proceed by sort of increasing complexity of a graph, and something that I showed you earlier involved the graph of the following form. Let me call it H-shaped graph because it has the shape of letter H, like this. So we don't know what the corresponding VOA is, but this was studied by Catherine Brinkman, Carl Mulbrook, and Anton Milish. And what they found is that this thing, this invariant, this corresponding Q-series for this particular gamma is high depth mock modular form.
Maybe you should move the screen up.
Oh yes, thank you. Yes. High depth mock object. So obvious question is it the character, or which kind of log VOAs have this kind of characters? So high depth refers to the following fact, that usual definition of mock modularity means that object is not modular, but it can be corrected in a certain way, and this correction is usually called shadow. So high depth is when this process repeats several times and you can have shadow of a shadow, and this can have depth n if there are n shadows of shadows. So as far as I know, this question is open from the VOA perspective. So one of the things that people, including our group and their group, are exploring is which logarithmic vertex algebras may have this sort of high depth mock modular objects as characters. So therefore, let me conclude this lecture by making, building on this sort of example, a list of problems. So problems or questions, as promised. So these again are not homework problems or questions. These are real questions. That they may be kind of reasonably hard and non-trivial. So mini projects for research. Perhaps if you solve it, it's worth a paper. And first and most obvious question is, but I'll put it with a star because it's very complicated. Is can we construct a log VOA labeled by gamma for any, say, negative definite gamma, even negative definite is good enough, such that it's invariant under Kirby moves. So I told you what Kirby-Neumann moves are. And one big question that will completely nail this whole part of the field, of course, but it's a difficult one, would be to just construct this VOA. So that's, if you wish, the wish list and the most priority item on the wish list. But it's pretty hard. So that's why I put a star on it. More practical question is to move in smaller steps and try to address first this one by one in terms of complexity. For example, start with some particular classes, infinite classes of graphs, analogous to how subject with Nakajima's observation developed past 94, and try to understand this class by class. So, like I mentioned earlier, for example, this trivalent star-shaped graphs are fairly well understood and recover something that we know well in the world of log VOAs. But next step involves this H-shaped graph and graphs with multiple high valency vertices. So that's something that's not fully developed and would be good to study. Another option, so question number 2, would be to which would help this sort of program, is to prove positivity of coefficients or find counterexamples. Actually, I was going to give a close cousin of this problem or question, but someone asked me yesterday about positivity, and I thought that this is really a good, indeed good question. I'm going to give a question number 3, which is analogous. So indeed, if we compute this Q-series for generic graph, or the collection of such, so we know that they have the form Q to the delta, and then there is this C0 plus C1 times Q plus C2 Q squared, and so on. So question is, are these coefficients, if we include the eta function, are all positive? I don't know a single counterexample, so actually I'm completely agnostic. This is an honest question. Either way, I think it would be interesting, because if some negative coefficients are found, it will indicate something derived. But if there are not, then probably proving it in full generality, at least for negative definite graphs, that's already a good exercise and non-trivial theorem, which at least I don't know how to prove immediately. What I was going to ask is a question analogous to this, also about the coefficients, and also of the same style, that explore the asymptotics of these coefficients. So either prove that so-called effective central charge, C effective, is equal to 1, or find counterexamples. And what is effective central charge? Effective central charge is the rate of growth of this coefficient. So as n goes to infinity, this coefficients in the expansion above Cn grow as exponential of 2 pi square root 1 over 6 n times some number. That's exactly this effective central charge. And in all examples that I know, especially arising from such graphs, this coefficient C effective happens, that controls this expansion, happens to be 1. And it's basically coming from the eta function that we put in the denominator of this Q infinity. And again, I don't know if it's true in general, or if that's the case, it would be good to prove it, because this C effective is a basic measure of VOA or CFT. Or if there are some counterexamples, then it would be good to find them and understand them. Again, either way, it's interesting. There is no prejudice, and I'm totally agnostic. There is no prediction either way for what it should be. But obviously, these sort of questions are precursors to understanding what log VOA should be for different gamma, and more generally for three manifolds. So next time we'll continue this exploration of this bridge, but I think I'm done for today, so I'll be happy to answer any questions.
Okay, so let's thank the speakers. Are there any questions?
Well, so I have a quick question.
Mm-hmm.
Is it true that the effective central charge of a triplet algebra is 1?
For triplet, I believe so, because basically its character, even with variable x, it's or one can evaluate it at x equals 1, basically forgetting it. It's going to be false theta function divided by q infinity. So in high rank analogous thing, there'll be as many etas as the rank in the denominator, so it will be just coming from those etas. Yeah.
So you divide by 1 eta because you're considering A1 case?
Exactly.
So if you go higher rank, you divide by
eta of tau to the rank. Yeah. Exactly.
Okay. Thank you.
Yeah, okay. I was going to ask the same thing actually. Do you expect in general that the effective central charge is equal to the rank of the gauge group? But, yeah.
Like I say, I don't know. So next time we'll move on to completely general three manifolds, way beyond this graph. So first of all, I'll try to explain more topology, why these graphs have anything to do with three manifolds. We're still just slowly moving in that direction. And then we'll write even more characters. So from this perspective, I mean, even these questions, which I phrased in terms of graphs, are kind of hard. So again, I honestly don't know answers to many of them. So I'm agnostic. Maybe even in territory of graphs, this effective central charge is not one. I mean, it's just a matter of understanding this integrals for generic enough graphs. Maybe counterexamples are not too far. But in general, that's probably not true. And one fun thing that I'll illustrate tomorrow is that here it looks really difficult to proceed. I mean, see, we kind of struggled with even reproducing only the simplest examples, really. Simplest families reproduce this triplet and singlet. So question is, okay, what do I have left for next lecture? So it's actually interesting that generalizing will be able to there will be completely new different perspectives, which will lead us to so-called fermionic form of characters but it's not visible from this narrow perspective of graphs. And then it's for sure that C effective is not going to be just one. So I don't want to make this conjecture. I don't think it's true actually, but I don't know if it's true for graph manifolds for this class.
Okay, thanks.
I have a couple of questions. I'm not sure how loud I am.
Yeah, I can hear you.
Yeah, but I was very loud apparently in the auditorium not long ago. So hopefully I'm not very loud now. I have a couple of questions. So presumably these first two are obviously hard. But in Tomoyuki's picture for 2 dimensions, he has some geometric operations like say gluing and then building a surface out of a pair of pants. And then he has the corresponding operations at the vertex algebra side. So I wonder if you have some guess or some wild guesses as to what this operation would be for. So now you started with the two things. One is the Kirby moves, and the other one is just at the level of the partition function, because you wrote it as a convolution of say theta functions that are explicitly characters of modules of lattice vertex algebras. So I wonder if the convolutions themselves have a counterpart at the level of modules and operations on vertex algebras. And the same for Kirby moves. If you have some basic objects, some basic vertex algebras, and then you make the Kirby move, if you have some wild speculation as to the analog of Tomoyuki's business, that is DRC reduction, for example.
Yeah, so that's a good question. This is actually just, I think it's basically exactly the question number 1. So that's what I see. I don't know the answer to this question, and I'm willing to bet money and offer bottles of wine to whoever is going to answer. But I believe the answer is yes to both parts of your question, namely that there is at the level of modules interpretation of this convolution, and yes, there is interpretation of this Kirby-Neumann moves. But again, that's precisely this difficult question, which it will be elegant if one can do it in one shot. Completely, it would nail this entire class of graph manifolds. The problem, and I'll show you the Venn diagram for these manifolds next time, it's already extremely big class actually from topology perspective. I mean, which is not surprising. I mean, you can draw any graph, decorate it in any way you want. It's way more than thinking diagrams or anything like that. So it's huge. And only small subset of this graph manifolds represent free manifolds, which are, for example, circle cross a Riemann surface. So for that's another small family. And in that case, there is indeed a way of understanding some of these VOAs in standard terms like extensions and BRST reductions. So in one of these papers with Fagan that I mentioned, we make this connection. But that's, again, very small class relative to this generic, even negative definite graphs. So next time, for instance, I'm going to allow positive definite and all kinds of things. But that's why I think your question is hard. It's basically question number 1 with a big star here. Maybe I should put 2 stars.
I have a very technical one, though, but a quick one. So the triplet algebra doesn't have self-extensions of simple modules. So you have non-trivial extensions of simples, but they're different simple modules. Mm-hmm. But it does have self-extensions of order 2. So you can have short exact sequences with 4 terms instead of 3 terms, mm-hmm. with the same simple modules in the end. And I wonder if this has something to play in this. I mean, if you have some physical interpretation for this, so you don't have self-extensions for this triplet algebra, but you do have degree 2 self-extensions for the triplet algebra.
That's a good question. I don't know. The best I can say is that here the triplet and singlet, in the traditional sense, the way we understand it, only appear in something simple which involves single single trivalent vertex. So, for example, if it would be vertex of valency 4, then we would already go outside of usual singlet and triplet. And I don't have a good answer to your question, but as a good politician, let me try to answer a different question, which may be slightly related. So somewhere here I mentioned this Fagan-Tipunian construction. And in general, so what we and many other people are playing with is exploring various generalizations where, again, there are two basic operations going on: taking kernels and doing extensions. So extensions is exactly what you suggested, and here one takes kernels not of a single screening operator, but of a bunch of them. But always there is, like in the beginning, there is some free theory. Usually there is underlying lattice, and this theory is a lattice theory. So it seems, and I don't have a good proof of this or even enough experimental evidence, but I could put this as yet another problem on the list, that the log VOA that appears in these manifold examples is related to the lattice lambda, which is lattice spanned on high valency vertices. In other words, we don't care about vertices in this graph of valency 0, 1, or 2, such as, for example, the end nodes of this graph would be valency 1, some intermediate guys would be valency 2, but what matters is valency 3 and higher. And it seems that this is defining the lattice, which may be helpful in addressing some of these questions, question 1, question 2, and so on. But again, this is very vague and heuristic at this point. So I think even making this more precise would be also quite valuable.
Thank you.
Okay, I have a question. So the singlet VOA is vastly spookier than the triplet VOA. The triplet VOA is C2 cofinite. It's Lie. So it's extremely nicely behaved, very tightly behaved. It's almost rational. It wants to be rational. And the singlet is a spooky thing, as I said. So, like it's an infinite orbifold of the triplet. And so, do you get? You might have said it, or you might be about to say it in your next talk. But how does the triplet actually come in here? Do you actually obtain some characters of the triplet, or is it just the singlet?
You probably, yeah, that's a great question. Thank you so much. And I didn't say it, and in fact, I wasn't planning to say it, so you give me a good opportunity. But it appears in the following way. So if you, in this construction, remember we defined this invariance of graphs, this z hat of gamma, by integrating over a bunch of x variables. So we also know, and the result, for instance, as written here, is character of a singlet theory. So we also know that, and I did write this somewhere, that character of singlet is basically analogous integral from the triplet when we integrate some x. So from this, you can actually guess what's going to happen. So in order to get triplet, you don't want to integrate one of the vertices in this graph, namely the central one. So if you don't integrate it, the corresponding x, so you integrate everybody else, but not this fellow, you get exactly the triplet character. So this has a meaning in topology, and in fact is very nice. So what you're going to get is a manifold which is not closed, but has a boundary. And next time, what we will talk about is how these graphs are connected to manifolds. We'll talk a little bit about surgery and corresponding algebras and so on. And for complements of torus knots, the corresponding invariance, the z-hat invariance, can be defined for, say, knot complements, and this will be important. It's actually extremely important for topology. They will end up being exactly the triplet. So that's why here, I guess I could say that we find both singlets and triplets. The only distinction is whether we take closed manifold or we don't finish one of the surgery operations. This is something that will come up next time.
Okay, thanks. That's interesting.
Okay, see if there are no more questions, let's thank Professor Gukov again.
Thank you.
Yeah, thanks once again. So that's the end of today's program. Tomorrow we have Professor Nakajima again at 8 a.m. and from 8 until 9:30, and then the rest of the day is free.